All right, everyone. Welcome to department seminar. Today I have Dr. Leigh Orf. Dr. Orf received his PhD from the University of Wisconsin in 1989. His advisor was Dr. John Anderson. Wrong date?
97.
Ah,
Bachelor's was 89.
my bad.
That's okay.
97. He is a former faculty member at UNC Asheville and Central Michigan University. Dr. Orf is currently a research scientist for the SIM/SECCs, where he studies severe thunderstorms. His hobbies include camping, hiking, homebrewing, and amateur radio. So please help me welcome Dr. Orf.
Thank you, thank you, thank you. And let's see if I can remember my password. All right. Wake up, little computer. So yeah, thanks for coming. I'm going to talk to you today about some of my recent research and see if I can get this thing to fill the screen right. Come on, dude, you can do it. Okay, that's better. So I use numerical models to conduct idealized simulations of deep waste convection. That's sort of my general research approach. I'm primarily concerned with problems that require a supercomputer to properly simulate. So I'm taking sort of a strange approach here. I come from sort of a computational utilization standpoint where I want to basically utilize the biggest supercomputers I can get my hands on and see if we can do something and learn something. I think most modeling studies are objectively under-resolved, and partly this is just due to logistics, computational power, the models we have, etc. I think that by increasing resolution in many cases we can actually get a clearer physical picture of what we're trying to understand. And this produces a data problem because these simulations create just tremendous amounts of data. And basic to my research is the use of lossy compression. I couldn't do any of this without actually going through some, you might say, contortions to get data, to get the I/O issue to sort of go away. And I essentially have got the I/O issue to go away with my model. Not quite go away, but the reason I do this is because things like this can happen. In 2017, my research team discovered what we call the streamlined vorticity current, which is air in the forward flank of supercells that may help to lower the pressure in the mesocyclone near the ground to help maybe even trigger or maybe maintain tornadoes. And last month, this paper came out. Now, Dr. Morgan O'Neill from Stanford University is the first author on this paper. I'll talk about this mostly today. But, I mean, that just happened. I can't believe it. So this is why I play with supercomputers. I discovered when you publish an article in Science, they write an article about your article, so you have a reference before you even actually have your article out. So I put a little thing together you can look at. But this is an important problem. And I'm going to sort of first talk to you about how this research team came together, because it's one of these cases where I felt like we had four perfect jigsaw pieces that came together to form a perfect puzzle. This is an issue for several different reasons, but anyway, I wanted to sort of talk about where this work began. So Morgan O'Neill, she was a postdoc at the University of Chicago when our collaboration began. She invited me over to the University of Chicago to give a talk on supercells. The University of Chicago is home to Dr. Ted Fujita, which is a really cool thing for me to go to where Dr. Fujita taught for most of his career. And yes, he's in this talk too, for reasons that will be pretty clear in a moment. The exact moment, at least in my mind, where this research began was a question that Morgan asked me at the talk, at the end of my talk. You can actually go listen to her ask the question because I record all this stuff. It's on my YouTube channel. But basically she said something to the effect of, if you expanded your domain more into the stratosphere, that would be really awesome because Tornado Alley is one of the primary sources of water in the lower stratosphere, and you could answer a lot of more global scale questions. When I heard that, I immediately thought, oh, this is awesome, because not only was I not super aware of this, but I wanted to increase the resolution near the tropopause anyway to look at the top of the cloud. We always, in our 3D numerical models, almost always use a vertical stretch that sort of makes the clouds near the top under-resolved. You know, we have not enough vertical resolution. So anyway, within a few months, we were formulating a plan to do some simulations. I had time on the Blue Water supercomputer at the time. Now it's Frontera at TAC. But anyway, that's sort of a little background. Other members of the research team, Kelton Halbert, he's a PhD student here. He's working with me. He's written some code that runs on GPUs. It's called Lagrange and offline flow trajectories. He uses my data format to go back and send trajectories forward and backwards through time at the model time step. You don't have to actually run the model to do this. The data's already been saved. Jerry Himsfield at NASA Goddard provided some observational data, and it was these, it was all four of us that basically provided input on this paper. And it was really just like the perfect fit for all of us. Okay, so the reason why I think this research is considered high impact is because AACPs, Above Anvil Cirrus Plumes, which I'll give some examples in a moment, but they actually have really important implications or potential implications in both weather and climate. We've discovered a mechanism by which we mix air from the troposphere and the stratosphere, and this is what causes AACPs. It's a hydraulic jump. It's not breaking gravity waves, or breaking gravity waves are probably not a primary force, at least in this case. So by properly identifying the mixture, how you mix water through the UTLS, I see this as being like a parameterization of the climate model someday. We're gonna figure this thing out. We're not gonna ever resolve it, but we're gonna at least do the parameterization, maybe get that mixing right. That's at least one thought I had. But really, the reason why I really wanted to study this before I knew more about this importance is that about 3/4 of supercells exhibiting these plumes, as seen from satellites, later exhibit severe weather, namely large hail or tornadoes. So AACPs could potentially, they're being used kind of today as an outcasting tool. You see them on a satellite, it gives you a 3 out of 4 chance maybe that you're going to have large hail or a tornado. Now I'm really kind of wondering about this relationship, but at least it's been observed. I don't know the physical mechanism, but that's what we're going to be looking at. So these are two sort of disparate but very, I think, important aspects that this research sort of crosses over. So here's a picture, I think, from the International Space Station, classic overshooting top. This isn't visible, obviously, since it was a camera. You can barely see in the visible the cirrus plume over here, and there's a thunderstorm anvil. We can assume the upper level winds are from right to left in this image. But that's basically what an AACP might look like from the side. Here's what they might look like from space. Kelton Halbert put this image together using GOES imagery. It's an RGB image. Let's zoom in on some of these features that we see. Here's this overshooting thunderstorm top. This is probably the best example on this one. There's your AACP. I love this because you can actually see a shadow cast from this plume onto the anvil beneath it. Pretty sure it's a shadow. Somebody else could. We could probably look at IR and figure that one out, but that's really kind of cool. Here's another storm, overshooting top. This is late afternoon, so you're getting those lovely shadows. There's your plumes, some other maybe plumy stuff going on there. And here's another one. You get the picture. That's what AACPs look like invisible. Okay, so we can go back to the 50s, actually, and talk about the origin of some of this work, namely in the physics of hydraulic jumps. Here's a paper from May 1954. This is a laboratory model. It's a two-fluid model. This is a solid surface, smooth solid surface. This is a tank. Fluid number one, there's actually a second fluid up here. You just can't see it. They're designed roughly to have density differences that might be applicable for, flow in the atmosphere. So this flow goes over this barrier here. You can think of this as maybe a downslope mountain flow. The flow actually is not encountering anything sharp here to cause this turbulence. It's actually just becoming supercritical. When the flow reaches a certain velocity, that's essentially, the flow can no longer, basically the internal gravity, you go faster than the internal gravity wave speed, and you end up with the hydraulic jump. And this is what we're seeing in our model as well. Ted Fujita took pictures, of course he did, from a Learjet, because that's Ted Fujita. And he gave everything names, as we know. This is from his paper on the Teton-Yellowstone tornado of 1987, very rare tornado, F4 that occurred in the Yellowstone. But this is actually not from just that storm. This is from stuff that he had already viewed from the airplane. So he gave these names, clean overshooting domes. I would assume here that this is an overshooting top, and this is a second overshooting top from an adjacent storm. I don't think this is evidence of a hydraulic jump. Curly hair cirrus, not really sure what's going on here. You've definitely got a dome and maybe something going on here. We call this fountain cirrus. He said this shot up like a fountain. Flare cirrus, looks kind of like evidence of maybe a Kelvin Helmholtz billow up here, not quite sure. And this is what probably matches us the best. The geyser cirrus. This shoots up like several kilometers. And this looks a lot like our hydraulic jump. This kind of looks like a mohawk on the top of the anvil. You know, it kind of shoots up.
Where's the flow potentially going supercritical? Like, I guess I'm just trying to compare to that
Under
picture
here,
you
it
showed.
would be under here. You wouldn't actually see where it is, but when I show you the numerical results, I'll at least show you what happens in the model. It'll be much clearer. Ostensibly, it's beneath the anvil. In fact, here's, well, depending on how you call the anvil. So here's one of his schematics. Overshooting, this is from an actual event, so this is a snapshot. This isn't meant to be a conceptual diagram. Overshooting top, maybe another overshooting top, and he knew it was a jump, because he's Vegeta, right? That's a joke. You would call it jumping cirrus, but it's actually from a hydraulic jump. And that's at least what our simulations tell us. But he'd already basically identified these things. He hadn't quite gotten all the dynamics worked out. Okay, so how do we approach this? Oh, no, I wanted to mention some of the prior modeling work done to study this type of AACP. So the top of the thunderstorm, I'm certainly not the first person to want to look at the top of thunderstorms by any means. Our own Powell Wang here at UW did some important work modeling in the early 2000s. Mullendorf et al. Did some similar work. And then coming up to Holmeyer et al. 2017, this is where we actually started. We started with their initial sounding. They also ran so we got 1 kilometer, 1 kilometer. Your horizontal grid, your vertical grid maybe is up to 250 meters. This is going to be really difficult. Simply the model is not able to capture frequencies that are that high. Let's just put it that way. The models can't do it. And in all these, one thing about the Holmeyer study, they used the Orf model. They found a relationship between the plume formation and the wind speed aloft, and that is something that we found as well. However, they attributed the AACP to breaking gravity waves that led to the plumes, and we found something that we think is different. So we used their environments as a starting point. They did a weak and a strong storm, sort of, and I'll explain this more in a minute. We re-simulated their environments after modifying them just a little bit. Again, I'll explain in a second. And 50-meter isotropic grid spacing. So we have cubic mesh, no stretch, everywhere. 2 soundings, strong and weak, 4,800 by 4,800 by 600 grid points, that's 13.8 billion. If you're wondering what the biggest run I've ever done, it's about 250 billion. This is a little challenging, but actually not as impossible as you might think. Here's our sounding. Here's potential temperatures and function of height.
Ask a question?
Yes, sir.
So on 2 slides before, I wanted to follow up on Larissa's question. So on the right, you have a wind profile. And it looks like from,
Are you talking about
I guess
here?
you have shear that is, the UDC is negative.
Are you talking about the wind profile over here?
Yeah.
Yeah, this, I looked at this.
So if you think of, in a one model,
This is kind of
the flow
backwards.
increases upward and it goes up and over a rising dome and then down on the backside, and then there's a jump. But that doesn't seem to be the case here. It looks like it's driven entirely by the storm itself.
Yeah, remember, this is Vegeta from the 70s trying to interpret what he saw. So this is his interpretation. You've seen Vegeta pictures before, right? He does this all the time. He has no actual evidence other than visual evidence of what's going on here. So I put this here just because he called it jumping cirrus because it's a hydraulic jump, et cetera, and it's from that paper.
So the upstream portion of the hydraulic jump is emitted directly from the updraft in this case.
I'm not sure that he actually identified how, if that is a hydraulic jump in that picture, yes, I would say. But that is just, again, that's a Vegeta schematic. I wouldn't take it too seriously in getting to the deep physics of it. Let me get to the results from the numerical, and I think it'll come together. So we start out with the classic, I think this is probably a Wiseman and Clump variant sounding, which is a hateful sounding, but anyway, it's like conditionally unstable boundary layer, absolutely unstable, moist here, dropping off a certain way. The only thing that differs between our 2 simulations is the wind profile. And this is where we differ a little bit from the Holmeyer work. We wanted to only change the unidirectional, we only wanted to change the speed of the wind, not the direction, in the layer that we changed. So the wind's, the actual direction in the shear, in the photograph is the same for both. For the weak upper level winds, We just cut them back linear like that. So
And
that's the only
what's-
difference.
What's your concept of where those winds come from?
Okay, this is designed to just strip back as much complexity as possible to come up with two experiments that show a difference, and the difference is only due to this. So in other words, we just try to make this, reduces the problem to,
Okay, but why choose those two profiles? Like what's,
that,
that's just what I'm trying to
I'll
understand.
get, Homeyer, the people whose work we are built upon here, did this work and found that with these two different upper level wind profiles, one of the storms produced an Above Anvil Cirrus Plume and one did not.
Oh, okay.
And we're essentially trying to reproduce their work so that we understand what's going on with the AACP, but we also have a control for another storm that doesn't produce one in a similar environment, but different enough that we can sort of talk about what's going on. So this problem took about 512 for Terra nodes for you computer folks out there, 56 cores per node. We had 8 ranks per node. We did 2 levels of parallelization. We saved data at the model time step, and the only way I can get away with this is because I spent a lot of time working on it. And it took about 1.5 days for the full simulation. The simulation with light I/O only took 6 hours. But then I will go back from the restart file and save data at the time step once I'm sure I have the simulation I want.
How big is your data file once you're done?
I'm using lossy compression, so it's not as impressive as it might sound. It's only about 20, 30 terabytes, I think. When I do all the time step stuff, I'm only doing it over a subdomain, and I compress it as well as but yeah, so if I hadn't done all that, it would be like a petabyte or 2, and that's, you just can't. It's just too much. So we find a similar relationship, but we attribute the difference in what's going on in these storms to a hydraulic jump. We essentially have a downslope windstorm forming along the lee of the overshooting top. And the reason why I think we need this kind of resolution to get this right is because the actual stream of air that's becoming supercritical is only about 500 meters deep, and give or take. And we have winds exceeding 100 meters per second. That was a surprise. These crazy velocities. You know, back 10 years ago, I would have assumed something is going CFL and I have to rerun it, but no, we're getting physical velocities that are exceeding F5 tornado strength. So this is sort of a nice schematic of a hydraulic jump with water. In this case, you have water and air in a tank. Water reaches supercritical velocity. The jump occurs. You have supercritical flow, your turbulence, and then a deeper subcritical flow. Conservation mass kind of explains that, but these things are actually exploited in dam design and things like that. When you want to get the water to slow down, you know, you can basically just have it go down a slope. It creates a hydraulic jump. Now, there may be some sort of barrier. I think they trigger these jumps sometimes, but you don't need it. You can actually find images out there of jumps occurring where there's absolutely no barrier to start it. This is work from, maybe you remember Rich Ratuno gave a talk here a couple of years ago. He was doing some work with hydraulic jumps over mountains. So this is a highly idealized simulation using the same model I'm using, showing, again, this is kind of the analogy here. This rotor, I'm not sure, I think, you know, you've got a solid ground here. It's a different setup, but it's not like hydraulic jumps in the atmosphere haven't been studied before, okay? But they always involve a topographical barrier, in this case, an idealized mountain. So here's some results. This is 40 minutes, 45-70, so this is the storm that produces the AACP. This is the storm that does not produce the AACP. You're looking at streamlines, isotropes, and moisture. Now we're focusing on low values of moisture because we're near the stratosphere, so we don't care about, you know, this is in parts per million by volume. And this thick little contour here is the 90 meter per second contour for that jet I talked about. And you'll notice that you're starting to see some mixing going on in the isotropes here, and then boom, it just goes and goes, and then you're starting to really get some moisture up into the stratosphere. Zoom in a little bit more there. But that's the onset, that's the AACP. The onset's actually somewhere between these two, or probably right about here. And then you'll see these little jets, these little jetlets, I don't know what you want to call them, but they actually, let's take a look at them at the full resolution. So we're going to show you the model grid. This is the model grid. You are seeing it. I want to show you because, again, I'm concerned about properly resolving things. These little jet things, you know, this is like 90, 100 meters per second. This is 1, 2, 3, 4, 5, 6, 7, 8. I think we're resolving it okay. But yes, I'll probably have to go to higher resolution to convince myself of that at some point. But I just wanted to show you the grid. That's a cubic grid, it looks like that. One of the interesting discoveries we made, and if you read the Fujita, we're trying to attribute this warm downslope, this warm region, anomalously warm region in the wake of the OT. And we see that within spades. It's subsidence, right? I mean, you're just basically subsiding, compressing the air. But look at the adjacent betas. You know, you got 200K adjacent to like 250K. Some very strong gradients. I mean, you're looking right at the tropopause, of course, or right at that barrier. I don't know what you'd call that. But it's a very sharp gradient.
That's temperature or potential temperature?
Oh, it is. It's temperature. You're right. Apologies. That's temperature. Yep.
Temperature.
So isn't that an axis of downwelling that gravity would fire that encompasses the whole field?
Probably. But let me get down to the nuts and bolts. Okay, so this is the water vapor field. Water vapor field. Yeah. So I'm again focusing on values that are pretty low. So here's your overshooting top, and I'll just let it go. So think of this as QV perturbation water vapor mixing ratio. You watch this thing form. Once it sort of starts cranking, remember that flare? Remember that flare cirrus that Fujita showed that kind of shot up kind of backwards like that? Looks a lot like that. So where do you think the maximum winds are right now?
The bottom of that red area.
Exactly. In fact, let's let them sort of come in. There they are. This is the U component of the wind.
How strong is that one?
100 meters per second, about 90 to 100 meters per second. We'll bring back, so you can see exactly right. It's right beneath there. It looks just like, I mean, this is as hydraulic of a jump as I've ever seen, right? I don't think anyone would argue what that is. Well, maybe you will, I mean, and I'll listen to you and we'll talk about it. But it certainly seems pretty straightforward. But it's also kind of important, I think. And you know, the implications, I think, are interesting. So this is much earlier on. Okay, this is before the hydraulic jump forms. One thing I want you to focus on, again, this is, you know, this strip here is like 70 to 90 meters per second. There's kind of a pre-existing jet that's sort of, you know, before the hydraulic jump forms, there's kind of like this sort of jet thing. And then right when it kind of breaks, I don't know cause and effect here, but once the jump forms, that's gone because of what a hydraulic jump is. You now have a much deeper region, a lot of turbulent stuff going on, and the flow is actually smaller. Here's W, the W component of the wind, updraft, downdraft, yay, gravity waves. And here's the jump kicking in. So we can look at what it does in each of these fields. And essentially it's churning up that interface and it's mixing. In 3 dimensions, this is the ice field. I'm focusing on large values of ice. So you wouldn't see this from your eyes, but I wanted to just sort of show you that's breaking wave, right? Pretty convincing. Still a breaking wave. You know, you can watch it in motion, you can stop it, but this is that region. So we're bringing in moisture from the troposphere, mixing it into the stratosphere, and some of this is irreversible, meaning once it gets there, it's essentially irreversible. They use the term irreversible. It's not necessarily meant if you take it literally, but it's going to take a long time for those molecules to get out of there. Now, let me pause for a second. This is the water vapor field as well, cross-section right through the jump. What's this here? This is a pre-existing blob, and I need to look earlier on in the simulation. My suspicions are that before the main jump really kicks in, there's probably something with the initial forcing of the storm, or maybe a small jump occurs and kicks this in, because if I'm being honest with myself, and hydraulic jumps are what are putting this stuff in the atmosphere, that's probably one of them, but we need to look back into that. There's already a plume that's sort of anchored into the stratosphere prior to this jump forming. Now this could be the result of the highly idealized nature of the simulation, I don't know. So here I'm shading the water vapor content with wind speed, so this is your jet, and now I'm focusing on low values of QV, so you can really see, you can really see it now. This is what more likely what you'd see, quote unquote, if you were actually encountering it, where these, perhaps these flows are indivisible. Obviously when you're doing volume line, you have a lot of control over things. I've changed the view now. Again, this is the ice field and now the vorticity field, focusing on values around 0.5 to 1. I can't remember exactly the contour, but when you're talking about turbulence, you want to pick a kind of a large value. So we can watch it happen. Again, there's some pre-existing stuff going on, and the turbulence or the vorticity masks everything else out. And there's a jump. And once it starts, it doesn't stop. And again, you're going to see this. It's interesting how some of these bits of turbulence up in the upper middle stratosphere kind of hang on. There's a lot to be learned here. But anyway, this seems to be the mechanism that's occurring. Here is David Cimarero at TAC, Texas Advanced Compute Center. He's working with me. I think we submitted this to supercomputing, but it's just another view. This is looking at, this is the ice field. So you've seen what happens. This is the model time step too, so it's super smooth, a little slower. But it looks pretty reasonable. I kind of like doing stuff like this. It can almost fuzz your eyes out and imagine it's a real cloud. And wait for it. There it is. So again, this is a volume rendered view. This isn't exactly what you see, but there's the onset of the jump.
What role does that upper level wind that you had the two initial conditions?
We haven't actually, yes, that's really the question. Why, right? What's the setup? What makes it such that particular storm? You get a standing wave, essentially, as opposed to like, the energy doesn't get dissipated in the same way. It kind of builds up. And this is the research part that we're pursuing now, to actually get down to that question, because that is the question. We need, the future, this is one simulation or two simulations. This is just identifying a new thing. As far as understanding it's all the details, that's the work that we're going to start working on soon. So as far as like where the air is coming, taking a Lagrangian perspective, this is work that Kelton did. So what we did, because we saved all the data on disk and we have code that can do trajectories forward and backwards in the model time step, we can do all sorts of neat things. So what we wanted to do is, these are Lagrangian parcels that meet one of the following conditions. The total wind speed, so that's the total storm relative wind speed, exceeds 110 meters per second within the jet before entering the hydraulic jump. So these are starting right around here. We're going to go forward and backwards through time. Or when the parcels make it up above 19.25 kilometers. So in other words, we're trying to show different regimes here. So yeah, these parcels primarily are anchored in the troposphere near the ground, but some of them come from the stratosphere, and that's kind of important, I think. In other words, we have some some dry stratospheric air coming down for the ride as well. It's not just tropospheric air. And we actually, if you want to sort of look at the mixing process in the Lagrangian perspective, these parcels are now shaded by potential temperature. And I'm colorblind, but even I can tell you've got something that's between blue and red here, right? So you're seeing mixing in the potential temperature. It's a kind of a neat way to show that, I think.
Excuse me.
Yes, great.
Do these kind of wind speeds ever show up on Doppler?
I don't know if anyone's looking for them. Has anyone actually looked for stuff at the top of the
No,
clouds?
I don't know. I mean, maybe they're not looking for it, but I think it would show up.
I don't think there's enough.
If you have a big
I don't know if there's
thunderstorm.
reflectors.
It's too thin.
It's too thin. There's a lot of reasons why it might be hard to see.
This is like water vapor mixing ratios of, you said
Point.
10 parts per billion.
Yes, exactly.
But you have ice particles mixed into that, right?
Some of them, yeah. Well, here's where you reach limitations of your microphysics at some point. I mean, do you trust ice microphysics in the middle stratosphere? I don't know. I don't know. Right? 'Cause I don't know if.
It's probably hard to see, but
Yeah, I don't know. There's hopefully going to be field work that's going to look for these things. Yes, Matt.
So in the previous slide, the acceleration from 50 to 100 meters per second as you go down, I think that, I'm working on the lower troposphere for hydraulic pumping for the and so you can conserve the sum 1/2 of u squared plus 2z plus p pi. And if you come down maybe, 3 kilometers, then I think from the overshoot, then I think you gain maybe that much kinetic energy. Is that, I don't know how, so I should have said, how do you think about that acceleration?
Yeah, what's causing the acceleration, or what I think about it? Well, I think about it is, I don't know, you've got this huge pulse that's pushing up against the stratosphere like a fountain, and it's got to go somewhere, so it squirts in some directions. I mean, that's really what I think about it. you can talk about all the stratosphere and inversion and all the interface, but essentially, you're throwing something up against sort of like a boundary. It's a soft, flexible boundary. And for some reason, some of the air is squirting away. And that's kind of how I'm looking at it. It's kind of a very kinematic, silly way of looking at it, but we're going to dig into this. I mean, we
When it
can...
hits the stratosphere peak and makes it a real prime, P-prime positive anomaly, which deflects it and creates a electric field.
Well, I'll tell you what, we save all the values of everything along these parcels, so we can actually go look at the forcing on them, and we can answer that question. I just don't have that answer, and Kelvin, I don't think he's here today. So, but anyway, no, those are great questions and great points. Really, this work is just sort of like, hey, we found this, and we're kind of at that stage at this point. We haven't done a whole lot of analysis. Now, I do want to talk about some observations, and this is, at some point, Morgan talked to Gerald Hemsfield. I don't know him personally, but he had this, he had some radar data showing an actual, this is just this blown up. So here you have what looks a lot like the Kelvin-Helmholtz billow. We see similar things in our weak storm, and this is just to show plausible relationships more than anything. In this bottom diagram, notice that the blue and red are kind of backwards, I guess. Up in the stratosphere, they do things differently. Your updrafts are blue and your downdrafts are red. Morgan told me that's the way they do it, and I was like, okay. But that just, if you're used to the other way around, just try to look at that and understand. Same goes here. So you've got your overshooting, let's see, distance on this. Anyway, most of this is just to show the relationship between these two things. So we have things that look reasonable in the observations. And now here's the last real slide, and this is the one that kind of really is interesting to me because it's something I've never really considered. Okay, so there's a lot of information on this small slide. So we're going to look at the total mass in tons of water that goes into the stratosphere during the simulation. Now, obviously, we're eventually going to run into boundaries and stuff. But we made the domain super big, and this is during nothing has left the boundary. It left the domain at this point. We stopped the storm, and the slope of that line, who knows how it would go. But anyway, this is for the strong storm, the solid line. For the weak storm, again, weak upper winds, strong upper winds, is the dashed line. Frozen material is in this little star, little snowflakes, and vapor is in little dots. So what this tells us is, we're calling the stratospheric middle world the region between the following isotopes. Let's see, it's the lower stratosphere versus the upper stratosphere, basically. Middle versus over. She's calling overworld, like getting up into 25 kilometers above the ground. So what we found was, actually, the upper levels winds with weak, the storm with upper level winds that were weak actually puts more water substance into the stratosphere, but it's the lower stratosphere. The jump storm cranks water into the middle stratosphere, where it does not get to come out. So that's the basic takeaway from here. Even though the actual total amount of ice from the weak storm is more than the strong storm in the, let's call it the lower stratosphere, middle world, the upper stratosphere, or I guess, I don't know, I'm not much of a stratosphere guy, so just look at these theta lines, that's what he's just calling them. We get this thing shooting up like crazy. So in other words, the jump is shoving air into the middle stratosphere, where it's not going to come out, right? It's just not. For all intents and purposes, it's irreversible, okay? And I think that's interesting. We've also sort of put a number there. This number is important to climate people, like how many kilotons from a storm. And I think our result is about twice the value that was considered before for some of these storms. But again, we've got 1 or 2 simulations, so it's not time to make grand statements about this. The main takeaway here is, yes, strong supercells hydrate the lower stratosphere. No doubt about that. Strong supercells that exhibit hydraulic jumps and AACPs, they hydrate even higher up, okay? They may not put as much in the lower stratosphere, but they're putting more in the upper. So I think it has to do with the way the jump sort of, the flow just kind of stops and builds up and just cranks, as opposed to when it doesn't, it sends that jet that keeps going, probably a little bit of mixing along that boundary. So anyway, that's kind of, this is going to be interesting. This is of interest to people that are outside of my area of main research. So anyway, yeah,
have another.
Yeah, I know, I left a lot of time for questions, so.
Okay, I'll wait till you.
No, I was just gonna say, and I don't mean to be cute here, but this is really the takeaway. As you can see, I may not be 100% on the dynamics of what we discovered, but it's early days, it really is. But I know I've got some interesting things to study. So if you take the time to do this, interesting things can happen. And you can discover things that are new. I have actually put some supplemental material for this talk on my website. Just go to orf.media/AOS 2021. I'll get that up again if I can. I'll forget it. I'll write it on the board. Anyway, I'll get the talk back up and I'll answer questions. Oh, come on, don't be a ding dong. Oh, downloads. Okay. So any questions, any parts you want me to go over again? Greg, go ahead.
Yeah, have you looked for a relationship between the equivalent potential temperature in the updraft and then the eventual level that the moisture comes to reside at? Is the moisture actually being transported to higher potential temperatures than you would find in the updraft? In which cases there must be some diabatic process that's warming it.
Yeah, if you take a look at the article, there's a couple of figures I didn't include where we actually trace some things and do some statistical analysis. And I'm sorry, I don't have that up for me now, but yes, we have started to look at those things. And yeah, but I'd have to bring up the paper and to get the figure.
You're saying there is diabatic?
Well, mixing is a diabatic process, right?
Mixing is, yeah. But normally mixing is not going to produce more potential temperature than the ingredients
I see what you're
that
saying.
went into it. But it could if you're mixing between very high potential temperature and a low potential temperature, perhaps brought together by momentum or something.
All right, let me see if I can answer your question. Since we got some time, anyone else have any questions while I'm doing this? Just go ahead.
So the diabatic part of it is, it's not any condensational heating, but what kind of radiative scheme are you using?
We're not using, oh, you're gonna hate this. We don't use radiation. Why bother? We're only doing it for like an hour, right?
Well, but, I'm wondering what would be the radiative effects of those
Oh, I know.
clouds on the whole thing?
Oh, I know, and the problem is when you turn on the radiation scheme, it takes like 700 times longer to
but
run.
it's,
I mean, I know it's important, but it's like,
you're perturbing the system, and there's going to be a radiative.
oh, there certainly is. I know, it's just, where's that figure? Something in the supplemental materials, I think.
But
There's one figure I want to show you guys. This one here. I think this is kind of getting at what Greg's asking. Let me see if I can get this to go.
It's going to be the radiative.
Okay. So we trace change in temperature. So this is some of the parcels that went fast, the jump parcels. The change in initial temperature and potential temperature is a function of the parcel initial potential temperature at 40 minutes. So start to finish. So we have parcels that, here's their initial potential temperature, and then their final, and same for those three diagrams. So take a look at that, and maybe you can tell me if that answered your question.
Not really, because you're talking about potential temperature, not equivalent potential temperature.
Theta E? Okay.
Or equivalent potential temperature using ice,
Right, theta,
which is a little
theta.
higher, yeah.
Right.
So,
No, we didn't. I think we did this on purpose. I think we did this on purpose because we just wanted to keep it simple to start. Again, this is like a 2,000-word paper. This is not an exhaustive scientific paper. This is we discovered something paper. The rest of the research, and that's great that you're asking these questions, but these are things that we're thinking about. I'm thinking of Morgan who wrote this. I think we talked about this. We decided to just stick with theta just to keep it simple. Because there's all these different thetas there's theta E, there's theta E like you said with ice. There's different ways to calculate those thetas. We just wanted to avoid all that stuff because some reviewers could just say you didn't do theta E right and they're not going to want us to publish. So honestly, that's kind of why we kept it simple.
right, but I think it's an important concept. What I'm looking for here is it possible to increase the potential temperature through mechanical means, you know?
What's going
which-
on in the swarm there, yeah.
And maybe that's not even, you know, potential temperature is conserved, making some assumptions about the equation of state holding and all, but
Right.
maybe in some of these jumps, maybe some of that doesn't hold. Maybe you
Yeah.
are getting into some la-la land where it is possible to diabatically change the potential temperature over the ingredients that are.
I don't think so. I mean, we're gonna be doing all sorts of analysis. We're gonna do statistical analysis. I mean, we've got every single time point. We can do everything you can imagine. I don't think there's a bug. That's kind of what you're working on. We're not in the I don't know where La La Land would exist. I mean, what factor would suddenly kick in that's unphysical?
Well, so far you haven't shown anything that's above the ice equivalent potential
Yeah.
temperature. So, you know, the ice equivalent potential temperature could be 380, 390 easily. So, maybe that's all it is.
Yeah.
So it looks like the simulation is stable, but you did bring up CFL as a potential issue. You said 150 meters per second winds, 50 meter grid, and a third of a second time.
No, 100 meters per second, not 150.
I thought you said your maximum was 150.
No, 100. I think our maximum was at 110. And that's
Have you run it? Have you cut time step in half to see if you still get it?
Oh,
And I know that's an expensive experiment.
No.
But that you're getting.
You don't understand.
It's triggered by
No.
some small little.
No. For one thing, when CM1 CFLs, it blows up. You can watch the little things move across the screen, the giant diamond of anything. And
Yeah.
I've been there many times. No, this is not CFL. The only reason I mention that, look, I calculate the CFL at every grid point in the model, find the maximum one at every time step. We never get above like 0.8. In fact, CM1 has like a hidden CFL criterion whereby the saturation adjustment scheme does not converge when you have the CFL about 1 or so. We're using a rugged cut scheme that has like, you can have like 1.2, 1.3 for a CFL parameter and it's still stable. So in other words, I've sort of actually been conservative with the time step. We're nowhere near CFL anywhere in this model. When I said that, the first time I got my tornado and I started looking at what's going on at the top, I saw these values and I thought that had to be wrong because we just don't have winds that fast up there. But I think we do. I think they actually are. We just haven't maybe measured them yet. It's hard for me to concede that there's some fundamental issue here with this model. But we just have, like you said, we have not done all that research. We're working on that. It's just right now there's 2 of us. So yes, Matt.
I'd like to have a comment and then a question. You know, this is just absolutely fantastic, and it's so much fun to look at. So thank you, really. It's just wonderful. It might inspire a new sport. You know how surfers are always looking for something new?
Totally.
Get a big surfboard, and he's going for the Leigh Orf shortboard.
I totally get that. No, I know, it's great. There's one view I like the most too. That's just, if I can't find my video anymore. Oh, there we go. Yeah, this is, where is this view? It actually reminds me of surfing. It's this one right here. Yeah, this one I feel like, you know what? This guy's already surfing. Take a look at this one vortex tube. Watch it dissipate though. It's actually weird. So this guy, hey, what's going on, guys? I'm just gonna dissipate. What's up with that? There's probably something interesting going on there, or it's a bug like
It's all about this.
But anyway, no, I know it does look, but you don't want to hit that, man. You're gonna that's a real shredder right there.
So I was wondering if the westward tilt of that structure is purely because of the outflow geometry. There's a jet eastward with a negative shear above, or is it intimately linked to down low in this particular MCS? Is the flow coming in from the east and then up? So that you have tilted updraft?
Yeah, it's really not very
Does
tilted.
that can sort of impose a kind of gravity pattern that encourages the westward tilt? Or it may be the reverse, that once you develop this sort of pattern at the top, it can help encourage an inflow with the tilt in the bottom.
You know what? I'm not sure how much the top cares about the bottom. Once the air's gotten up there, somebody asked who reviewed the paper about the rotation rate of the updraft and whether you'd see, rotation at the top of the overshooting top. The top of the overshooting top is almost completely divergent. There's almost no vorticity up there. It's really, it kind of makes sense when you think about it, but it's very smooth. But as far as that orientation in this, I don't know. Again, That's a good question, but it is striking how much it looks like that one Vegeta thing. One of his many observations. So at least when I think ahead about where we're going to go from here, we need to explore this parameter space of when you get AACPs and when you don't. That's one of the things, because right now the operational folks are desperate for any nowcasting tool they can have for tornadoes, and AACPs are potentially useful. If a hydraulic jump is what causes an AACP, then we have to ask ourselves, what is so critical about the formation of a hydraulic jump that is intuitive about tornadoes and hail? Is it just the strength of the updraft, or is it, no, it's the strength of the updraft and the upper level wind shear? Why is that so important for tornadoes and hail? So, you know what I'm saying? Like, people using AACPs as nowcasting tools, I want to know why they're useful, not just that they are. And this is a step towards that direction, but I'm still not really convinced that they're super useful. I mean, I hate to say it, but
I actually think the climate avenue might be more fruitful.
yeah. Well, I'm going down both avenues, but yeah, that's the one that's
That
got
water
more.
vapor, mid-latitude water vapor flux and how, depth of storms will change in the future.
That's the big thing. I didn't mention the climate, because I'm not a climate guy. I don't want to pretend to be one, but that's the one that scares me in a way, because we've already identified the fact that we got a ton of hydration occurring over the, let's say, the convective region of the United States, other regions too. If we have more strong storms, injecting more water vapor into the middle stratosphere, destroying more ozone, letting more short-wave radiation in, letting more heating happen, there could be a potential positive feedback. Maybe it's a little esoteric, but it makes me wonder. I don't know.
I was thinking about that. Water in the stratosphere, usually people say it's super important for a drastic effect molecule by molecule of the greenhouse warming problem. But you're probably right, there's some influence on ozone. The Hawks profile peaks up higher, I think, for net loss. And I don't know if there's a super important part of ozone.
Okay, see, that's,
Low down, I think chlorine might be dominating.
okay.
It'd be more of the rate of heating from the water vapor.
From the water vapor.
And
That's
two
probably
methane plus water vapor is conserved in the stratosphere, so you're also, you're destroying water vapor and making methane. So that's what that rate is.
Okay. And I thank you
It's
for.
important.
Yeah.
Yeah.
I know this number is important for climate, and that's
And
why.
there's trends in stratospheric water vapor that people don't understand.
Right. So understanding what causes the moist, the hydration in the first place is important. So again, I'm focusing on a phenomenon right now. I'm just trying to get the phenomenon right. The implications of the phenomenon are taking years and years to unravel. I mean, that's just the way it goes.
Do you have any, do you have any hypotheses for why that upper level U wind profile makes a difference?
Yeah. Again, the physical, the actual full loop, no, we looked at this earlier, we came up with we did some posters and stuff, and Morgan is the lead on this, I'm the numerical guy. If you look at the paper by Holmeyer, you can look at his argument, and we've essentially, it seems to have something to do with the formation of a standing wave occurring prior to the formation of the jump. In the storm that doesn't produce the jump, the energy is just dissipated in a more diffuse way. In the storm that produces the jump, it just builds up in a certain way. So there's something going on, and we don't know what it is. It may have to do with reflected gravity wave energy coming down. That was one of our theories about how that energy is building up. It probably has to do, we don't know yet, okay? But we've already sort of identified there's a difference, but that's the research that is now ongoing. We're starting that research now because we don't know exactly why. Yes.
Yeah, I'm curious about like the maximum resolution that you can really observe or simulate these processes by, because that's going to kind of tie into like how you can like really validate them.
Sure. When I say validate, I want a plane to fly and find these things. And there's a field program, it's ongoing, I forget the name of it, but I'm kind of glad that this paper came out when it did because they have the opportunity to actually look for these now, assuming they weren't looking for them before. So that's what I say validate. Validate is it in nature? We haven't found this yet. Yeah, it's possible that this don't exist. It was possible that SVCs didn't exist and we found them too. Those things that, so that's good. These models, that's why I think something like this is a heck of a lot more basic and fundamental than the other thing. Some of the stuff involved with tornadoes is all very very nonlinear, very whatever. This is a pretty stable, rooted in some hydraulic theory. It seems pretty likely that this is real.
So I was just thinking about the pattern of gravity waves in the stratosphere, and at first it looks like maybe they're going through a turning surface, but I can't heat it because you got a weak east to the shear, and what you need for that is a super strong westerly. And so I think what you have is a really fine example of dispersion. Low down, those modes don't propagate energy upward very much. There's a spectrum, and you have a short vertical wavelength down in there, and up higher to the right, they're taller, because the energy associated with LZ big propagates upward faster.
And also, we're still running into the friggin' top of the model domain. I want to go into the mesosphere, man.
Yeah.
Well, seriously though, I mean, I don't know how far you can go, but 30 kilometers is how deep our domain is. Not many people are running compounds at 30 kilometers.
120 kilometers. GFS goes up to 120 kilometers.
Oh, that is good to know. So they've got different physics up there, probably.
Yeah.
Okay. But I like that that's a thing. Great.
I would think that the depth and the whole idea of why these things occur in some storms and not others would be tied to the lower level dynamics. And
I hope so, because that makes it more useful.
And the way, I mean, not necessarily the conditions at the surface, but the conditions throughout the storm, and that I think supercells are so different from other cells in that they have very adiabatic updrafts, that the updrafts conserve everything almost entirely, but in varying degrees depending on the supercell. So I'm guessing that the ones most likely to send things up high would be the ones that come up with the most adiabatic updrafts, and therefore the highest equivalent potential temperature over ice. You see what I mean? So assuming there's nothing goofy going on, like I said, with non-meteorological flow,
Right.
I think that it's really just tied to the theta E, the potential theta E high, the theta E of the ice coming up in the updraft, and how much of that can reach the top of the storm without being entrained.
I hear what you're saying. Yep. That's easy to calculate. And thank you. We'll put that in there. We can just, we basically, when we do this trajectory stuff especially, we can just calculate stuff on the fly. So we can just go back and look at theta EI along those parcels and see if it's being conserved or how it's changing. Thanks. That's good. Anything else? Like I said, if you're link,
Lee, go ahead, send that to everyone at AOS.
okay, sure, yeah. And it's a copy of the article and stuff, so just don't share it outside of science and get pissed off. 'Cause, but you know how it is when you're sharing articles.